Okay guys, so welcome to our next lesson. Today we are looking at section 4.1 day 4, which deals with exponential and logarithmic functions. And in day 4 we're going to focus on finding the extrema, the intercepts, and the asymptotes of these functions. And so the first thing we're going to do here is review a little bit what extrema and asymptotes are. And remember, when we use that word extrema, we're talking about either the minimum of the graph, so minimum looks like this, or the maximum, which would look like this. And remember, there can be local minimum or maximum. So for example, a graph like this may have a maximum here and then a minimum down here. So you are allowed to have both of them in the same graph. You could even have more than one maximum or more than one minimum in the same graph. A horizontal asymptote, just like any asymptote, is going to be a line that the curve approaches, but that it never actually touches. So for example, if I had a graph like this, okay, I would have a horizontal asymptote right here, because you see that my curve is approaching that line, but it's never actually going to touch it or cross it. Now let's talk about finding our intercepts. In order to find the x-intercepts, we can very easily do that in the calculator. We just go to second, trace, and then remember our x-intercepts are just another way of saying our zeros. So if we go to second trace 0, that is the same exact thing as finding our x-intercepts, or where the graph crosses the x-axis. To find the y-intercepts, this is a little bit different, because there is no calculation that we can just put into the calculator. So we have to do a little bit of thinking and investigating ourselves. So we press second graph in the calculator, and we want to look at that table, because the y-intercept happens where x equals 0. Okay, because if I were to have a graph here, let's say my graph looks like this point, this y-intercept, is going to take place where x equals 0. So that ordered pair might be 0, 3. So my y-intercept would be 3. And that's why I'm going to find my table, see where x equals 0, and now I know what my y-intercept is. And let's take a look here at our first homework problem. So this is example number 65 out of page 398 in the textbook. They're asking us to use a graphing calculator to find the local extrema, the y-intercepts, and the x-intercepts. Investigate the behavior as x approaches infinity. Remember, infinity just means that we're going to the right, and as x approaches negative infinity, so just means as we're going to the left, and identify any horizontal asymptotes. So this is the equation that your book would give you to graph, right? So just make sure that in y equals in the calculator, we put in that 2 plus e to the x minus 2. And then we would end up with this curve down here. Okay, so I've already graphed it for us, but make sure when you're doing your homework, you have to have your calculator. You have to be able to graph these. So the local extrema, remember, for local extrema, we're looking for a minimum or a maximum. In this curve, I do not see a minimum or a maximum, so I would write none for local extrema. For y-intercepts, here's my y-axis, here's my x-axis. I do have a y-intercept right here. So make sure, even though it looks like you might be able to tell me what it is just from the graph, make sure you go to the table, okay? So hit second graph, and second graph will take you to the table. And remember, that y-intercept is going to take place where x equals 0. So here, where x equals 0, my y-intercept is actually a decimal. So if we had just looked at the graph, we might have thought the y-intercept was 2. But notice, looking at the table, we see specifically that it is not 2. My y-intercept is actually 2.14. I'm going to round to the nearest hundredth. Okay, so that's why looking at our table is so important, because sometimes the graph can be misleading. So here we have found our local extrema and our y-intercepts. I'm going to go to the next slide to take a look at our x-intercepts and our horizontal asymptotes. So here on the next slide, we have the same question. Okay, notice my equation is still the same as the last slide. We're just doing part 2 of it. Now we're wanting to focus on finding the x-intercepts and the horizontal asymptote. So here is my x-axis, and my curve does not cross the x-axis. So for x-intercepts, you would just tell me none. For horizontal asymptotes, okay, do we see how, yes, we do have this invisible line that my curve is approaching, but it's never touching. Now, if we want to find this asymptote, we can trace our curve, and as you trace it, you will see that it's getting closer and closer to 2. So my horizontal asymptote would be y equals 2. And usually the horizontal asymptote will be a little bit easier to identify. So there is our x-intercepts horizontal asymptote for this problem. Let's try a new one here. So for number 75, again, we're going to be looking for those extrema, the intercepts, and then any horizontal asymptotes. This is the equation that the book will give you. Please make sure when you graph this into your calculator, you need to put parentheses around that numerator. If you don't, the order of operations will be misread. So when you enter this into y equals, make sure you have those parentheses around the numerator. And when you graph that, you will get this blue curve that we have down here that I already graphed for you guys. So for local extrema, again, that means we are looking for a minimum or a maximum. This graph pretty obviously does have one. So for local extrema, I would go to second, trace, and since my extrema here is a minimum, I would go to second, trace, and then I would press minimum. If you accidentally press maximum, then the calculator will tell you the wrong result. So to find the local extrema, press second trace in your calculator, then select minimum. It'll ask you to go to the left of the minimum, to go to the right of the minimum, and then to guess. And so you do want to guess, and when you enter that in, you will be told that the minimum is 0, 1. So my local extrema would be 0, 1. You can clarify that it's a minimum if you would like to. For my y-intercept, remember my y-intercept is where it crosses that y-axis, and I can see right there where it's crossing as well. And if we look at the table, we want to find where x equals 0, and so my y-intercept is going to be 1. So I have my local extrema and my y-intercept so far. I'm going to go to the next slide where we can investigate the x-intercept and then any asymptotes. So here we have the same problem. Okay, now we're just going to be focusing on the x-intercepts and the horizontal asymptotes. So my x-axis is right here. And does my graph cross this x-axis? It does not. So for my x-intercepts, you would just write none. Now for my horizontal asymptote, again, is there that invisible line that the graph is approaching but never crossing? It does not have one, so for my horizontal asymptote, you would also tell me none. And now we are going to go to day 5. Again, it's only going to be a couple of slides, but this lesson today is a 2-parter. And in day 5, we are going to switch gears a little bit. We're going to focus on compound and continuous interest. So we're going to be given 2 specific formulas. And make sure you write these formulas down or that you go back in and look at the PowerPoint as you do your homework, because you will need these formulas to complete your homework. My first formula is the compound interest formula, and it is right here. So let's talk about what all these letters represent. A represents the ending amount. Okay, so this letter A is going to be my final amount after I get the interest. P, the reason it's a P, is because it stands for the word principal, and principal means the beginning amount. When you're talking in finance, your principal is always the beginning amount. R is going to be the rate. However, the rate must be a decimal. So keep in mind, usually they'll tell you that the rate is growing at 8%. However, we cannot just write 8 and call it a day. We have to turn this percent into a decimal. So remember, my decimal point would be here, and to turn that percent into a decimal, I go 2 to the left. So 8% as a decimal would equal 0.08. And I think most of you are familiar with that, but just a little reminder, okay, that rate can never be a percent. Turn it into a decimal. The letter M over here represents how many times you are compounded per year. And the directions will tell you it is compounded daily, it is compounded weekly, it is compounded monthly, okay? And the letter N represents the total number of compounding periods. So total, because if you are compounding for 1 year, you're going to have a lot less than if you compound for 10 years. And let's look at our first example here, and that way we can clarify some of these as well. Okay, let's look at our problem. Suppose $4,000 is invested at 11% compounded weekly. How much money will be in the account in A, half a year, and in B, 10 years? So that's why I have two equations here. I'm going to split my screen in half because I'm going to have to set up one equation for part A, one equation for part B. So for part A, I'm going to put A equals P is my principal, or my beginning amount. I'm starting with $4,000. So I'm going to put in 4,000, 1 plus, R is my rate. I am being told the rate is 11%, but to turn that rate into a decimal, I go over 1, 2, so I would have 0.11. So for R, I'm going to put 0.11 over, remember M is how many times we are compounded per year. So if I have compounded weekly, how many weeks are in a year? I have 52. So I'm going to put 52 here for M, because if I have compounded weekly, that would be once a week, so 52 times a year. For the letter N, this is where it gets tricky. N is the total compounds. Now in example A, I am being told that this is going on for half a year. Half a year is 26 weeks. So that means I only had 26 compounds, because if there's 52 weeks in an entire year, there's 26 in half a year. So I hope that made sense going through all those steps. Now that we have this equation set up, you can put that right into your calculator. What you will need to do is include an extra set of parentheses here around the fraction. Remember, we always put parentheses around fractions. And so my final answer here would be $4,225.92. We would round to the nearest hundredth because we're dealing with money, and money always goes to 2 decimal places. So after half a year, this is the amount of money that I would have, which makes sense. If I started with 4,000, I should have a little bit more if I'm gaining interest. Now let's go to part B, which tells us the 10 years has passed. So I am still starting with my principal of $4,000, because in both situations, I'm starting with the same amount of money. I have 1 plus my rate is still the same at 11%, so I'm going to put 0.11. M, remember, is the number of compoundings per year. Now, I'm still being compounded weekly. So how many compoundings is that per year? 52. Here's where it gets interesting. N is the total compounds. In example B, I am being compounded, or the interest is being compounded, for 10 years. So if I'm being compounded weekly for 10 years, so I'm going to write that here, weekly for 10 years, what does that mean? Weekly compounding means 52 times a year times 10. So that would be a total of 520 compounds. So that's what I'm going to put up here for my exponent. Now that I have this as my equation, I can just enter that right into the calculator. Make sure that you put parentheses around your fraction when you enter that. And so what you would get for your final answer is $12,002.71. And we always want to look at our answers to make sure they make sense. Okay, if after half a year you have $4,225, after 10 years it makes sense that you're somewhere around $12,000. Okay, 10 years is a long time, so you've been able to accumulate a lot of money. And there we go with our first example. Now let's take a look at graphing and how we're going to use graphing. If we are told that $3,000 is deposited into an account earning 8% compounded daily, and at the same time, $5,000 is deposited into an account earning 5% compounded daily. Will the first account ever be worth more than the second account? If so, when? So if they're asking for when, they're asking for time. Okay? They want to know when will it ever be more. And notice what we have to do. We're going to have to come up with equations for both of these situations. And then we're going to have to graph. So we're told that 3,000 is deposited into an account earning 8%. So for this first equation, this is going to be my scenario number 1. My principal is going to be 3,000. In parentheses, I'm going to have 1 plus this 8%, move the decimal place over twice, and I get 0.08. So my rate is going to be 0.08. M is the number of times compounded per year. So if I'm compounded daily, how many times per year is that? That is 365 times per year because there's 365 days in a year. N is how many total compounds? I don't know what the time is, right? That's what the question is asking me to find. So for time, I'm going to leave my variable x. Okay? Now let's go to my second situation. For my second scenario, my principal is going to be 5,000 because now I'm starting with $5,000 in the second scenario. I'm going to have 1 plus, my rate is 5%, so turn that into a decimal by moving the decimal place over twice, and I get 0.05. This one is compounded daily. So for the letter M, that's how many times per year. If I am compounded daily, that is 365 times per year because there's 365 days in a year. Remember, the letter N is the total number of compounds, but we don't know how much time has passed, so I'm going to put the letter X there. Now we graph this, okay? In your calculator, you would put this first equation into y1. You would put this second equation into y2. Remember to put that extra set of parentheses around your fraction. And then you graph them. And so notice I've given us the graph already over here. Okay? That is what you will see in your calculator. Now it's very important to be able to identify which curve goes with which equation. And notice, this curve starts lower. So this is the curve that's starting at $3,000. Okay? This is the curve that's starting at $5,000 because it's starting higher. And the question is asking, when will the first account, so when will this account that starts at $3,000 ever be worth more than the one that starts at $5,000? And notice, here at the beginning, it's still worth less, but all of a sudden they intersect, and now my red one is worth more. So in order to find that place of intersection in the calculator, we go to second trace, and then we hit intersect. And when we do that, we'll be given this ordered pair. Now, which part of this ordered pair do we care about? If we are solving for x, that means I care about the x. So x is representing the time. So this 6,216, what units am I working in for time? I'm working with daily. So your final answer would be x equals 6,216 days. So this here at the bottom would be your final answer of when would the first situation be worth more than the second. It would be after 6,216 days. Phew, good job following along with that one. All right, we've done our first type of interest. Now let's look at continuous compound interest. And so here is our equation for continuous compound interest. A, just like in traditional compound interest, is going to be the ending amount. The letter P is still going to stand for principal, which is the beginning amount. R is still going to be the rate. Remember, our rate has to be a decimal. Now, how do you know when to use this equation instead of the other one? Because it's going to say that phrase, compounded continuously. If you are told it is compounded daily or compounded weekly, then we use our other compound interest formula. If it is compounded continuously, then you have to use this formula that involves the letter E. Remember, the letter E is our special constant value, okay? And you can find this in the calculator by doing second and then the division symbol. Okay, that's where you can find the letter E in the calculator. T is the time in years. So here in the exponent, we have T for time. Let's go ahead and use this formula now. We are looking at money growth here in number 89. If you invest $5,250 in an account paying 11.3% compounded continuously, there's our magic phrase that tells us to use this equation. How much money will be in the account at the end of A, 6.25 years, and B, 17 years? So again, notice I'm going to split my screen. I have the equation written twice so that we can go through it. Now, in this PowerPoint, it's a little bit easier because I'm telling you what equation to use. On the quiz and test, you'll have to know which equation to use. You will be given a formula sheet, but phrases like this, compounded continuously, that's what's going to be your hint for what equation do I use. If it's compounded continuously, then I want to use that letter E. So let's get started with setting up my equation. For my first scenario, scenario A, with 6.25 years, my principal is going to be $5,250. That is the starting amount. Then I just put the letter E, because that's a constant. It's just always the letter E. For my rate, I am being told 11.38%. So to make that into a decimal, I go over 2 places, and my rate would be 0.1138. For my time in situation A, they say 6.25. So I'm just going to go ahead and put 6.25. And so if I put all of that into my calculator, 5,250 times E to the power of 0.1138 times 6.25, I end up with $10,691.81. Again, I'm going to go to 2 decimal places because I'm dealing with money. So the investment is growing. After 6 years, I have $10,000. So far makes sense, right? Your money should be growing after 6 years. So now let's go to part B, which is asking us after 17 years. So my principal is still the same. My principal is still that $5,250. The letter E is still the letter E. My rate is also still the same, 0.1138. Here's what changes: the time. How much time are they telling us has passed in example B? They're telling us 17 years has passed. So I put 17 in there. So now I'm just going to enter all of that into the calculator. And so when I do that, I end up with 36,336.69. And again, does that answer make sense? That after 17 years, I would have 36,000? Yes, right? I have a lot more money than I do after 6 years. Okay, guys? And so there's example number 89, similar to what you will see on your homework. Here is your homework assignment for tonight. Notice for 1 day 4, you have 66 to 76 evens. For 1 day 5, you only have 3 problems, but it is a 2-part answer. Okay, it's going to be just like the last example we just did, where there's a part A and a part B. So please make sure in Google Classroom, under homework, you go into the right section and you submit your homework. Okay, make sure everything is labeled clearly, that your question numbers are labeled clearly. At the top of the page, you put homework for 1 day 4 so that I can give you the proper credit for that. So thanks again, guys, for joining me for this lesson, and I will see you for the next one.